Good evening, everyone. Welcome to the University of Houston. Tonight's the third in the Energy Symposium series, Critical Issues in Energy. I'm Dan Wells. I'm the Interim Dean of College of Natural Sciences and Mathematics. This series allows us to take a closer look at key topics in energy and bring experts to the forefront to help us understand the scientific basis of some of these issues. Tonight's topic is climate change. Is it a real threat? I want to mention our one remaining event, which will be on March 4th, Renewable Energy. That's our last in our series. I hope everybody turns out for that event. I really appreciate everybody turning out for this event, considering the weather. We've had great, overwhelming support from the community, from our industrial partners, from faculty, from students, from alumni. I just want to thank you all. It's been a really successful series. I especially want to thank the students. There's a lot of students in the audience. You know, you students, you're our future. You're the one that's going to take over from us when we're all gone. So I'm really glad you're paying attention and you care about these issues. I also like to recognize our two media sponsors for tonight, the Houston Business Journal and Houston Public Media. They've been instrumental in broadening the awareness of our event. So thanks to our media sponsors. So after some initial comments from the speakers, we're going to have a question and answer period. You all have these index cards on your chairs, or you can get one if you don't have one. We ask you to put your name, and then just note whether you're student, faculty, staff, alumni, industrial community. We want to try to get questions from different segments of our audience, not all just one segment. So that's why we ask you to do that. And then there'll be someone down on the aisles to pick up those questions as we go along. To start tonight's event, I'm pleased to introduce a special guest. A few years ago, under the guidance of President Renu Couture, the university identified energy as one of its key strategic focuses for education, research, and technology incubation. President Couture's vision and leadership has been instrumental to the Energy Initiative. We are pleased to have her with her tonight, and I would like to invite President Couture to come up and say a few remarks.
Thank you, Dean Wells, and good evening, everyone. I'm sure you all have turned out here because the weather is so bad and you're wondering, is it really climate change? So I think it's kind of was appropriate. I was in McAllen this morning because we opened an office there, admissions office in McAllen, because we are serving that region significantly. Now here today, this is the third symposium in this series, a special symposium here. This has been the vision of the Energy Advisory Board. Now, Energy Advisory Board is one of the jewels here that we have because they have been advising us and getting us on the path for truly making a contribution to Houston's oil and gas and energy landscape. I have 3 board members here from my Energy Advisory Board, and I do want you to meet them. David Ram, who is the chair of the Energy Advisory Board, is right there. David, come on, you can stand up. Thank you. Then I have Steve Greenlee here. Steve, thank you, from ExxonMobil. And I have Corby Robertson here. Corby, thank you very much for being here. How many of you are students here? Would you please wave? Okay, thank you. The reason I asked you to identify yourself is because as I walked in today to the VIP reception, I heard the best comment, which I hear, quite often, but to hear it from one of the speakers here is very special. And what the speaker told me is, he says, I have gone to many universities, talked to many students, and your students here were the best and the smartest one that I have ever met anywhere. So, to you, the students, after all, it's all about you here. So thank you for being here. Thank you, everybody, for being here. And let the debate begin, and let's just learn some more about climate change. Thank you, speakers, very much, and thank you, the sponsors. We appreciate your support.
Thank you very much, Chancellor Couture. I'm Ramanan Krishnamurthy. I'm the Chief Energy Officer, and that's perhaps the cheapest way to become a CEO, especially in academia. And thanks to Renu, I have that title. So she came up with that title and said, this is for the energy initiative. That makes a lot of sense to do it. Want to also recognize one other board member who's here, Lee Tillman of Marathon Oil, who joined us on our board. So before we move much further, I want to introduce a couple things with our social media. We're trying to do a lot of things with social media. Beware, Dr. Couture has her iPhone, so she's going to probably tweet about you, and you will probably be taking photographs of and tweeted about. So, and we've got our own Twitter hashtag that's associated with Houston Energy. Please do follow us on that. Also, we have got a Facebook page that highlights what we're doing in the energy space. So please do like us on Facebook. So before going any further, let me introduce our moderator. He is Barry Lefer, who is an associate professor of Earth and Atmospheric Sciences. He's also the associate chair of the department, and he's a real stalwart in the energy and the climate change space. He has been instrumental with some of the most dynamic courses I've heard about, and those were some of the students that our speakers visited with earlier today. He used to be at NCAR in Colorado before he joined the University of Houston, having done his Ph.D. from the University of New Hampshire. Without any further ado, Barry, thank you.
Thank you very much. So Ramanan deserves a big deal of credit for making this event happen. And he invited me to help select the speakers and to figure out how to cover this really interdisciplinary topic. And the name, Is the Threat Real, is a little bit loaded perhaps. And so what we really meant to say is, what are the risks? What is the threat? What are the risks associated with climate change? All of us deal with risks every day, and in the business side and at the university, we understand what risk management means. And so talking to the speakers last week, we had a conference call and we came up with these systems. Climate change impacts ecosystems, the food supply, infrastructure. And when you're talking about food supply, infrastructure, and energy supply, you're really talking about the economy. And so there's economic impacts or risks associated with climate change. And finally, we also realized that this is a political and social issue as well. And so we're going to try and cover some of these topics, and I'm hoping that your questions will fill in the gaps if there are any. When I teach intro climate change to 150 students, the first day of class, the first slide is this one, that I'm a geophysicist. The data that we're used to dealing with, that you all have seen the graphs, I'm not going to show any graphs, is that the Earth's temperature has warmed over the last 100 years, and that concentrations of greenhouse gases in the atmosphere have increased as well. And it's pretty well understood that the increase in these gases is due to human activities. And so these two pieces of data from direct measurements are related by basic physics. And so we have known for over 100 years that greenhouse gases like CO2 will absorb heat being radiated from the Earth and then re-radiate that in all directions. Some of it's going out to space, some of it's going back to the ground. This, among other things, will cause the Earth to warm up. But climate change is more than just a temperature increase. And so, like I said, it impacts the economy as well. So we want to start this discussion with this assumption that, and this is from the National Research Council, climate change is occurring and is very likely caused by human activities. And the purpose of these three gentlemen here in their talks is to talk about the risks. What are the risks to human and natural systems? And because we're educators, and this is a university, really, the overall goal at the end of the night is that we improve your climate literacy. And so with that, we're talking about climate change will bring economic and environmental challenges as well as opportunities. And if you still have questions after you leave this room, I really want to encourage you to go visit the National Academy of Science. They have a nice site about America's climate choices. Just Google America's climate choices and you'll get this site. Several in-depth papers. So the first speaker is going to be Dr. Richard Feely. He's going to talk about ocean acidification. And so really, what has happened so far? CO2 has increased in the atmosphere. As you'll learn, CO2 dissolves in water. It forms a weak acid, carbonic acid. So we'll learn how is that impacting these marine ecosystem, what's the economic impact of that, and a little bit of forecasting for the future. Our second speaker is Dr. John Nielsen-Gammon, the Texas state climatologist. He's going to say what is the risk of doing nothing, of just continuing business as usual. What's the climate forecast? That's his job, and he gets to do this every day, speaking to the public. And then our third speaker is David Hone. He's from Shell, and he's going to talk about what are our regulation options and what are the risks of regulation, and really talk about this idea related to carbon prices. So I'm going to introduce each speaker one at a time. And Dr. Richard Feely is a NOAA Science Fellow at the NOAA Pacific Marine Environmental Laboratory in Seattle. He has a BA in chemistry from the University of St. Thomas in St. Paul, and an MS and Ph.D. in oceanography, in chemical oceanography from Texas A&M. His major research areas are carbon cycling in the oceans and ocean acidification processes. He's got he's a member of the advisory board for the International Ocean Acidification Coordination Center. He's authored more than 230 peer-reviewed research articles. He's has many awards. A couple are the Department of Commerce Gold Award for Research in Ocean Acidification. He's been awarded the Heinz Family Foundation Environmental Award, and it's a very prestigious honor, as he's a fellow of the American Geophysical Union. It's fewer than the top 1% of scientists in this area get that award. So without any further ado, Dr. Richard Feely. Thank you.
Well, thank you very much, Barry. That's a wonderful introduction. And I'd like to thank everyone for allowing me to come here back to Texas. I have fond memories of my postgraduate school days in Texas, and it's a great time to be back. And it's nice of you to greet me with my Seattle weather as well. Ocean acidification has been known by scientists for more than 50 years from a geochemical perspective, but it's only come to light in the last 15 years or so from a biological perspective. So it's a very new science. And what I'm going to do is bring you up to date on where we are, what we know, what we don't know, which is just as important, and what the future holds for us. So that's the menu for tonight. So I'll give you a little 101 on ocean acidification. I'll explain why our coastal regions are particularly susceptible and what the present and future holds for us. Now, as everyone knows, through the last 250 years or so, the burning of fossil fuels, coal and oil and natural gas, has released CO2 in the atmosphere. We've actually released about 2 trillion tons of carbon dioxide into the atmosphere. And so far, about 28% of that carbon dioxide has been absorbed by the oceans. Now, what's interesting is carbon dioxide is a gas that reacts with seawater, and it forms a weak acid called carbonic acid that lowers the pH and decreases the carbonate ion. Carbonate ion is particularly important for making the calcium carbonate shells of many of the organisms we like to eat, such as oysters and lobsters and so forth. Now, what we know from the IPCC reporting process is that mankind releases, on average now, about 9.5 petagrams of carbon, billion metric tons of carbon into the atmosphere from fossil fuel burning and deforestation. And about 45% of that remains in the atmosphere. It increases CO2 concentration in the atmosphere. About 27% gets taken up by the land. This is the regrowth of forests. And another 27% is taken up by the oceans. Ultimately, about 85% of that carbon dioxide will end up in the oceans. What this is our sister laboratory, the Earth System Research Laboratory, has 60 atmospheric stations throughout the world. They get samples. And on the right-hand side of the map is the zonal map of CO2 concentrations. On the left-hand side is the South Pole, and the right-hand side is the North Pole. And this is the average concentration along latitude bands. If we run the movie now, we'll see the changes from year to year of that atmospheric CO2. What you see is the release of atmospheric CO2 in the atmosphere in the northern latitudes, primarily, because that's where all the industry is. And as the uptake in the summertime, CO2 is growing every single year. It grows at a rate of about 2 parts per million per year on average. This decade, last decade, was less. So we're actually seeing an increase in the growth rate of CO2 in the atmosphere, about 2.9% per year. This is due to the increase in the burning of fossil fuels throughout the global world. This plot is a very fascinating plot. The red line on top is the very famous Mauna Loa record, the longest record started by Dr. Charles Keeling in 1957. And right underneath that record of the atmospheric CO2 is the ocean CO2 levels at Station Loa, right above. Mauna Loa is down here on the Big Island of Hawaii, and Station Loa. This has been maintained by the University of Hawaii for the last 20 years or so. And what you see is the increase in atmospheric CO2 concentration from the burning of fossil fuels is mimicked by the ocean CO2 increase as well. They increase at exactly the same rate. And from those data sets, we then can calculate the changing pH, the decrease in pH of seawater from these data sets. So from measurements alone, we monitor the changing pH, and that decrease is about 0.02 pH units per decade. So from measurements alone, like at stations like this throughout the world, we know that the ocean is acidifying, no doubt. Now, the chemistry of acidification is very simple. You all know it because when you take a glass of pop, that's what you're seeing. Those bubbles is the CO2. The CO2 reacts with water, form carbonic acid. This is the same thing as that you would have in your lime juice. And that carbonic acid then would form a hydrogen ion. A hydrogen ion is what lowers the pH. That's the acid. That hydrogen ion reacts with a carbonate ion. Carbonate ion is what forms calcium carbonate shells. And it decreases the concentration of carbonate ion. It uses it up, takes it away to form bicarbonate. Now, we know that from the data sets that we have thus far, plus the ice core records, that the average pH of seawater in the open ocean in the pre-industrial was 8.2. Now, pH is a logarithmic scale, just like the Richter scale. So a 1 unit change in pH is a 10-fold increase in the hydrogen concentration. So that pH has dropped from 8.2 to 8.1, which means the hydrogen concentration has increased by 30% since the beginning of the Industrial Revolution. Carbonate ion concentration has already decreased 16%. By the end of this century, in a business-as-usual scenario, we'll see a pH drop another 0.3 or 0.4 pH on average throughout the world oceans. That's a 100 to 150% increase in hydrogen ion concentration throughout the world oceans. And that carbonate ion concentration, the blue line, will have decreased by 50%. Now all the animals that make calcium carbonate shells are struggling just to get the carbonate. So what we know for sure from the IPCC process is that approximately 28% of the CO2 that has been generated by humans since the mid-1700s has been absorbed by the oceans. Ocean acidity has increased by 30%. Ocean acidity will continue to increase by 100 to 150% by the end of this century. And the current rate of acidification is at least 10 times faster than anything we've seen over the last 50 million years. So not only is the amount of acidification important, but the rate of acidification, because those organisms have to adapt or evolve to these rapid changes that are taking place. Now, another important geochemical process, again, you all think about it. This is the Tums reaction in your stomach, when you put a Tums in your stomach. And the calcium reacts with carbonate to form calcium carbonate. And this is how shells are made for oysters and lobsters and coral reefs. And it turns out the geochemists have a term called the saturation state. And when that saturation state is greater than 1, they can produce their shell or skeleton. When it's less than 1, the shell begins to dissolve. My job is to study where that dissolution begins to occur in the oceans. That's what I do for a living. And it turns out, this is critically important, to whether or not the organism can respond to ocean acidification. Common calcite minerals are calcite and aragonite. Aragonites are things like corals and pteropods, and calcite are things like foraminifera and coccolithophorids. Now, what we've learned from studies throughout the world during the past 2 centuries, that most of this anthropogenic CO2 is still in the upper part of the water column. It's in the upper 1,000 meters of water column. Why? Because the ocean circulation is so slow, it hasn't gone down to the bottom of the ocean where it can be neutralized by reaction with sediments. So it's still in the upper part of the water column. It takes about 1,500 years to go through the circuit of the ocean. And it still resides there where most of the organisms live. So my job in a paper I published in Science 204 is to show where this saturation depth is, where the shells will begin to dissolve. And you can see in the Pacific Ocean, it's relatively shallow. In the high latitudes, it's also very shallow, 200 to 400 meters. In the Atlantic Ocean, it's still deeper. That's where the water is forming, so it's still deeper. So it's big differences between the Atlantic and Pacific for both aragonite and calcite. This map shows what that saturation state will look like in 2100 on the top panel compared to the pre-industrial. The blue colors means it's good for producing the shells. Saturation states are high. When you get to the cyan colors, you begin to get lower calcification, slows down. In the tropical regions, you see it slows down by as much as 50 to 60%. That means the coral reefs have a hard time calcifying against sea level rise. They got to keep up with sea level rise, and they're slowing down the calcification. In the high northern latitudes and the high southern latitudes, the entire water column is undersaturated, saturation state less than 1, which means they're dissolving. So the organisms have no place to go because they're dissolving. This is their ocean of the future. Here's the pH changes for the same conditions. The lower panel shows the pre-industrial. pH is about 8.2 or 8.3. Upper panel is the pHs throughout the world ocean at 2100, 7.7 or so. Major changes that we are predicting for the future. Now, in addition to that, in coastal regions, you have to consider if this water is sitting at about 200 meters off our shelf, that's below the shelf break. But if the water can get pushed onto the shelf by some process, it can affect many of our marine resources. Along the coast of Washington, Oregon, and California, this process occurs every springtime. The winds come from the northwest, and when they do, that pushes the surface waters offshore, pulls the water along the bottom, and so what happens is this acidified water moves along the bottom all the way to the beach, into the hatcheries, and then out at the surface. And we see this every year. So what are the impacts on marine organisms? We study this in laboratory settings, in laboratories with single organism and CO2 levels. We can study it in mesocosm experiments. We can study it in the ocean by putting little capture tents over and adding the CO2. We do this many places. What we have found is that coral reefs are particularly sensitive to acidification. They're one of the most sensitive species of all, and the addition of increasing temperature from climate change and CO2 together makes them more susceptible than just one or the other by itself. We also have many calcifying species that we humans love to eat, like oysters. So they're people food. And also fish eat calcifying organisms. 50% of all the fish in the world eat calcifying organisms for food, like shrimp and pteropods here. Also, these coral reefs are ecosystems to provide rook reefs for many of our fish and shellfish. In fact, 25% of the fish on Earth spend some time in a coral reef ecosystem. Now, what we do know is that in these places where there is upwelling on our coast, where we see pHs that you might expect to see at the end of the century right now, we are seeing major impacts. The shellfish industry on the west coast of United States found that in 2006, they were seeing their oyster larvae, the oyster created in big vats, and they grow these oysters to make seed. And the seed are about this big. And they grow them in these vats, about 20 million oyster larvae in a vat. They were finding that these were dying off fairly rapidly in 2006 and 2007. This created a crisis because they couldn't provide enough seed for the seafood industry as a whole. And this was causing them to have a complete collapse of their seafood industry within a few years if it continued. $110 million industry, 3,200 jobs in the state of Washington alone. And what we found was that when we went in there and we had Maria Cantwell, our senator, provide some stimulus money to put the CO2 sensors in the vats themselves, the same way we do on the ships, we found that when the pH was low, they were dying within 2 days. When the pH was high, they were just fine. So here was a perfect example of acidification and its impacts in the future. And by adjusting the pH of the water coming into the tanks, we were able to save that entire industry such now that their productions are coming up. So developing adaptation strategies for acidification worked in this situation. Now here's another example of an open ocean snail called a pteropod. The clear translucent pteropod on the left-hand side is what they normally look like. On the right-hand side is what happens under ocean acidification. You can see the shells dissolve at a high CO2 concentration within about 29 days. If you show the movie for that, this is what the pteropod looks like in the field. This is a free-swimming snail. He lives at about 100 meters at depth and swims to the surface at night to eat phytoplankton. And this is what salmon eat. And the first year salmon, this is about 50% of diet of these pteropods. So they're very important to the food chain. But what we have learned is that calcium carbonate forming shells such as coccolithophorids and pteropods, the pteropods eat the coccolithophorids and then the pink salmon eat the pteropods. They prefer the pteropods for food. So you can see this is a food chain, a fairly short food chain, and it's very, very important. Some of the estimates by our colleagues in the National Marine Fisheries Service have suggested since 50% of their diet are these pteropods, a 10% drop in pteropod production could cause a 20% drop in mature salmon weight. So we are now getting an understanding of how these processes might work. Another example of an ecosystem effect is a study that was done in Papua New Guinea at Milne Bay, in which CO2 was emanating from the seafloor. You can see the CO2 bubbles rising out at the surface there from a volcanic system. This was pure CO2. It lowered the pH to 7.8, which would be the level of pH that you might expect to see near the end of the century. 43 of 45 species of corals died in this particular environment. That's the impact of acidification on these coral reef ecosystems. Remember I said the coral reef ecosystems, they have a net worth to the world society of about $375 billion a year. This is a best estimate that just came out this year of the potential impacts of acidification on a variety of different commercially important species. From the mollusks on the left-hand side, you can see about 60% of the mollusk species are affected by acidification, and that's about $24 billion industry. You can see that the echinoderms, the sea stars, and the crustaceans, the lobsters, are also impacted. Lobsters are about $37 billion. Fisheries are also affected. Finfish are affected, $65 billion for finfish. So you can see this is a food security. 1 in 7 persons in the world get some of their protein from the oceans. So this is a food security issue in a major way. So here's the risk of acidification, how our marine ecosystems and how our food security would be impacted. This last slide shows a list of all the different physical and chemical and biogeochemical processes that are known to be affected. I will only tell you one story. A very interesting work done in Australia with clownfish, those Nemo the clownfish, pointing out that when you place clownfish in high CO2 levels, their neuroreceptors change. So instead of avoiding being eaten by the predators, they swim towards their predators. So here's a physiological response that's being impacted. We're just beginning to understand some of these responses. I think I'll end there. Just keep in mind what we're seeing in the oceans because of climate change. It's a warmer world, it's more acidic, and probably will be less diverse. Thank you.
All right, now looking forward, John Nielsen-Gammon is a Regents Professor at Texas A&M University He's in the Department of Atmospheric Sciences. He's the Texas State climatologist. His bachelor's degree is in planetary sciences from MIT. His master's and Ph.D. is in meteorology, also at MIT. Fresh out of graduate school, he was hired by Texas A&M. He has many prestigious titles. One is the former president of the International Commission for Dynamic Meteorology. He was chair of the American Meteorological Society Board on Higher Education. His research is on both the large and local scale meteorology, air pollution meteorology, drought monitoring and prediction. I should mention he has a blog with the Houston Chronicle called Climate Abyss, and he's also a founding member of the Climate Change National Forum. And finally, some of his awards, he has a National Science Foundation and White House Award, the Presidential Faculty Fellow Award. He's a fellow of the American Meteorological Society. And closer to home, he's a weather hero in 2012 of the John C. Freeman Weather Museum right here in Houston. Please join me in welcoming John Nielsen-Gammon.
Okay, so about 65 million years ago, a moderately sized asteroid or some similar object struck the Earth near what is presently known as the Yucatan Peninsula. Caused a variety of consequences, including the extinction of the dinosaurs. Should we regard that as a bad event, something unfortunate? Well, if you're a dinosaur, you probably would. But if you were a dinosaur, you wouldn't be here, so that's moot. And if you're a human, which most of you seem to be, you can probably thank your lucky stars that the dinosaurs got cleared out of the evolutionary web so that we were able to move up to near the top of the food chain after due time. And it's hard to imagine something happening to the planet that's more catastrophic than that. And yet the planet did just fine. So at least we can put a boundary on the severity of man-made climate change. It's not the planet's survival at stake. The planet's going to be here long after we're gone, whether or not we have a role in how long we stay. The threats or risks come with respect to the things we value about the Earth and about ourselves and about our society. So, for example, many or most of us value nature in the sense of the variety of ecosystems that we encounter in Texas and around the world. And those ecosystems, unlike how we tend to imagine them, have not been in their present state for millions of years. In fact, Texas looked very different just 10 or 12,000 years ago when the Earth was coming out of its last glacial period. So we have a very short perspective on timescales for things. Yet, we still, for a variety of reasons, tend to feel a sense of responsibility for not, in a sense, messing up the world. Apart from the benefits we gain from the rich diversity of life on the planet, we, in a sense, value the planet, and to the extent that we want to make the world better than we found it, we also don't want to make the Earth worse or less diverse or cause a bunch of extinctions unnecessarily. Now, since climate change has happened in the past, then why should present-day climate change be any different or be a concern? Well, first off, our infrastructure, our society, is built on the basis of the present climate. We design things to fit with where the climate situations we have, the typical frequency of rainfall and drought, the seasons, the temperatures, the wind patterns, and so forth, the different crops that can grow in particular areas. Nature left to its own devices would have ecosystems migrate north and south as the climate changes, whether it's natural or unnatural. However, our society has compartmentalized the world, so we now have different countries, different states, and so forth. And we've built roads, we've converted natural systems to farmland, we've left vestiges of the natural ecosystem in individual places. So any climate change that happens now, it's much harder for the natural systems to adjust to it because man at the same time has put many barriers in its path to prevent it from adjusting. So one of the risks associated with climate change is the risk that climate change in combination with the other stresses we put on the ecosystem are going to cause extinctions and harm to the natural environment and things that we value both rationally, spiritually, and so forth, because this climate change is not only relatively fast, but also taking place in the context of the rest of what we've done to the ecosystems. We also have a hard time as humans adapting to climate change now compared to in the past. There's some evidence that rapid climate change in the past associated with glacial and interglacial cycles actually helped humans get their smarts and learn how to adapt and so forth. And we have a history of, we originated in Africa, we migrated to Europe, Asia, and so forth, basically trying to find suitable climates to live in and learning how to live in other climates. Human migration is no longer a simple matter. We've broken the world up into nations and so forth, and no longer do we even really tolerate people who live a nomadic lifestyle. They've been essentially confined to individual pieces of the globe. So it's going to be very hard as places where food can be grown change for the society that's built up around the current agricultural system to change along with that. And, we're talking about climate change, and I haven't yet said anything about global warming, because for those consequences that I'm focusing on, it doesn't really matter how the change takes place or why the change takes place or what direction it takes place. It's a matter of the fact that the system is in a certain equilibrium, adjusted to a certain climate state, and any rapid change in either direction is going to have certain consequences, many of them negative. Now, if we're trying to adapt to climate change, then we have to deal with the specific threats of the specific types of climate change that we're going to see. Part of the problem of doing that is that the existing climate is the only one for which we have data for, or at least solid data. We've got some data from paleoclimate proxies going back thousands, millions of years that tell us something about what the climate was like. But as far as details, about all we can say is right now we're close to as warm as we have ever been in the past 10,000 years. If we go up another couple degrees, we'll pass another threshold. Last time the Earth was mostly ice-free was about 125,000 years ago, and we had we were about 1 or 2 degrees warmer on average around the globe. And there weren't mass extinctions, there weren't massive releases of methane hydrates or other possible wild cards in the climate system. So the reason that 2 degrees of warming has sort of been established as a maximum target is not because we know that there are going to be many bad consequences beyond that, but it's really beyond the point at which we know that there's not going to be many bad consequences. And it's that uncertainty, the fact that we're going into unexplored territory, that represents a risk that's really very difficult to quantify. I want to conclude by looking at some particular projections of climate and focus on a potential risk to Texas in particular. Now, these are the results from climate models, which I like to think of as simulations of an imaginary planet whose climate is very much like our own. So it doesn't represent reality. It also doesn't represent a forecast because it only includes a few factors affecting climate. It doesn't include what might happen to volcanoes, what might happen to the sun, and so forth. And I'm also going to be focusing on what amounts to basically the worst case scenario that was considered by the IPCC in its latest report. So the magnitude may be, or is likely to be, less than what I've shown, but at least this shows the pattern pretty well. And we've sort of caught on that a lot of the changes are basically scale with the amount of greenhouse gases that we add to the atmosphere. So here's the pattern for rainfall. I can show you temperature, but temperature, the Earth warms up everywhere. That's a nice, simple one. Rainfall is difficult because rainfall is caused by air rising, and if air sinks, well, it's got to sink somewhere if it's rising somewhere else. So you tend to have winners and losers with rainfall if you like to attach a value to rainfall in that sense. In Texas, we're sort of on the borderline. Things get drier to our south. In Mexico and Central America, according to almost all the climate projections, they get wetter to the north in Canada. Evaporation is the other side of the water equation, how much water you're losing. And that tends to go up in most places. Well, the amount of evaporation tends to increase in most places. And when you deal with the consequences of all that, for, say, society, there are two big uses for water. One is for drinking and irrigation, so let's call it managed water. And the other one is agricultural usage for not just for the ecosystem, but for what we call dryland agriculture. So for water supply, about half of the water we get in Texas comes from surface water, comes from runoff that flows into reservoirs and so forth. And you can see, according to this, Texas is one of those areas in the United States that looks like it's a problem as far as the amount of water that's going to be available in the future compared to today. Like most of the climate change impacts on Texas, it's not the leading impact on water supply. The increase of population in Texas is the leading impact, but it's an additional factor that makes the planning even more difficult than it would be with just a growing population. And along the same lines, the amount of water that stays in the ground and is available for plants to use is also projected to be going down in the future, as more so in Texas than in most other parts of the country. So those are a few of the sort of the more easy to pin down consequences of climate change. The risks are not only the ones that we can foresee, but also, because we are going into uncharted territory, the ones that as yet we can't. Thank you.
All right, our last speaker, and I want to encourage you all to write down questions while you're paying attention to David. Because we're trying to go with short 10 to 15-minute talks and then have lots of time for questions. So David Hone works for the Royal Dutch Shell Company and is a climate change advisor in their CO2 team. He has joined Shell in 1980 after graduating as a chemical engineer from the University of Adelaide in Australia. He has worked in refinery technology, oil trading, shipping, amongst his new job for Shell. David was chairman of the International Emissions Trading Association from 2011 to 2013. He works closely with the World Business Council for Sustainable Development and has been the lead author in a number of climate change publications. Please help me welcome David Hone.
Right, well, thank you very much, and thanks to the university for inviting me here to speak to you. So climate change, is it a threat? And you'll see I left out the word real. I'm not sure that's really the debate. What I like to talk about is a different aspect to this, really, and not so much the physical threat, but the regulatory and policy developments that are going to occur around the world and how they might constitute a threat, both to those that are on the sort of receiving end, but also to society more broadly. And you know, are they going to actually help us resolve this issue? Because ultimately that's what we need to do. So we shouldn't be surprised about what we've heard so far. It's really just physics and chemistry. Perhaps this is a book that some people use, I don't know. But if you open it up, you'll see all the standard stuff there. And this is an issue that, it has a solid science of over 100 years. It goes back well into the 19th century. And even in the 20th century, back as far as the Johnson administration, it was an issue that was starting to bubble up into the political world as scientists were advising politicians that this is something that they might want to think about. So this is already 50 years ago, and we haven't thought about it perhaps nearly enough, but nevertheless, it's starting to gain some traction today. But you might have noticed the issue's become a bit political. And I'm not sure that this is because of the science. It's because the solution lies with government. And it lies with government intervening in the energy system, intervening more in society than it has. And this is something that upsets people. And many see this as a threat. But governments are starting to take this issue very seriously. And back in 2009 and then in 2010, despite the fact that we look at the international process and think it's somewhat flawed, they nevertheless came out with text at the Cancun UNFCCC meeting where they agreed that 2 degrees C was an important milestone and that we should try and keep the rise in global temperature below this. And we heard about this from the last speakers. But I think it's important to start to put some context around this. What does 2 degrees C actually mean? Because that's really what we're going to have to deal with. And so we're an impatient lot, and we tend to think of climate as something we better act on today, or we better have a target for 2020. We better think about what it means for 2050. These are important milestones, but this is a long, slow, drawn-out issue that's going to be with us right through this century. And what it really means is, for 2 degrees C, and even there's some subtext there that they'd really like to look at 1.5 degrees C, which becomes a very challenging target. This is an accumulation issue. We've already heard that the CO2 is emitted and it tends to just accumulate in the ocean atmosphere system. It doesn't go away very quickly. And so the 2 degrees C we can equate to the release of 1 trillion tons of carbon. Now, there's lots of uncertainty around that, but that's the core of the issue. It's about releasing carbon out of the geosphere and putting it into the ocean atmosphere system. And over the last sort of 250 years, we've used up about half of that amount. We've already emitted about 580 billion tons of carbon and put it into the atmosphere system. And certainly, given the rate at which we're using it, by the early 2040s, we'll have gone past this trillion tons. By the end of this century, we'll have used up what are the current reserves of fossil fuels, but there's undoubtedly more to come, and this process just keeps going and going. And whilst there's a recognized uncertainty, there's a fairly distinct relationship between the peak warming that we're going to see at some point in the future and the cumulative emissions of carbon over this very long period of time. And it's about 2 degrees C per trillion tons over a sort of a modest range before it starts to plateau out a little bit. And so that sort of implies that this is all the coal, oil and gas that we can ever use, because otherwise we'll exceed this 1 trillion tons. So does this represent a threat? It certainly represents a risk, not only for energy companies that produce this, but from society at large that consumes and uses it to power today about 80% of the world's infrastructure, industry, vehicles, and everything else. So governments are starting to move on this, and they're moving actually quite rapidly. We think it's a very slow, drawn-out process, government regulation, but in 1990, if you look back, there was almost nothing. Governments were certainly talking about the issue, but nothing had really happened. By 2000, they created the UNFCCC, this is the Framework Convention on Climate Change, and had negotiated the Kyoto Protocol. It hadn't been ratified, but we hadn't started actually seeing the implications of that throughout the world. Now, the Kyoto Protocol is a system that's built on the basis of carbon allowances, the evolution of a carbon price in the global economy, and that starts to change the way in which we look at the use of fossil fuels. By 2010, a number of parts of the world had started to act on this, and North America was very much part of that. If you go to British Columbia and Alberta, if you go to the northeast states of the United States, if you go to California, all of them have carbon price within the economy. Many other parts of the United States have a carbon price that's not visible within the economy, but still there because of some sort of CO2 legislation. Australia has implemented a carbon price, although it's equally thinking about de-implementing it, but Europe has implemented a carbon price as well. And so we roll on to 2015, and what we see is a much broader application, not only of carbon pricing, but of carbon regulation. And this is looking forward just a year, but we all know that the Obama administration today is looking at the implementation of carbon regulations right across the United States. And Canada have said that they would follow a US approach. And we see it appearing in Brazil, in Chile, in South Africa, where they're talking about a carbon price. In China today, where there are 5 carbon pricing approaches being developed in different parts of the country and different trading schemes to test out different ways of implementing regulation. Kazakhstan, actually, surprising, everyone says, oh, who would imagine they had carbon pricing? But that is something that's being implemented there today. So it's all starting to happen. And so it really raises the risk, could future climate legislation put downward pressure on the value of coal, oil and gas companies? That's a risk that we have to think about as well. And I think you'll find that many coal, oil and gas companies are responding to that risk. They have, and this is an example of the sort of the framework that sits in Shell. We have a mission around CO2, we have a set of objectives, we have a number of activities ranging from talking with legislators about the types of legislation that's coming, to looking at how the company might respond to this and the types of technologies it needs to develop, the way in which it has to start to think about the operation of refineries and industrial processes that it has around the world, and so on. So all of this is going on inside companies like Shell and certainly many, many other companies around the world. Not just oil and gas, but also other types of industries as well. The cement industry is an example. Large producer of CO2 has spent many years looking at this risk and thinking about how it might manage it in the future. So there's also a risk behind the politics and the legislation that's coming. And as a sort of a simple picture of what this risk is that, you know, we spend 20, 30, 40 years negotiating, putting into place lots of policies, and the emissions continue to rise. And that we recognize that it becomes increasingly difficult to attain this 2 degrees C, to limit the total emissions of carbon to atmosphere to the trillion tons that I talked about earlier. And it's possible that, you know, many of the populist measures that we talk about today, they might sound good. They sort of ring true to, in a sense, that you think they're going to reduce emissions, but do they really do that? So we talk about renewable energy, we talk about energy efficiency, we talk about the carbon intensity of economies, but we very rarely talk about actually reducing emissions and doing away with them, because that's what the issue is all about. And we come along to a technology that doesn't get a lot of airtime. despite the fact that it's quite possibly the critical technology that we're going to have to implement on a very large scale through the rest of this century, carbon capture and storage. So this is taking the CO2 and actually putting the carbon and putting it back where we found it. And one of the issues we find is that it addresses many of the problems that we have with some of the policies that exist out there today. So if we go and put a wind turbine up outside this university and it starts feeding these buildings, does that result in a reduction in global emissions? Now, certainly the university uses less electricity from the grid, so somewhere on the grid there's a bit less coal burned locally today. But where does that coal go? It probably gets exported and is used by somebody else in the world who still hasn't actually got any energy at all. Or it actually even gets used later. Because after all, this isn't about the emissions today, it's about the accumulative emissions over time. So if you build that wind turbine on the grounds of the university, you've got to be sure that the coal that it displaced never gets used ever again. And that's a hard ask. But you could use it if you put the CO2 back in the ground. So CCS is important because there's an endpoint in this discussion. And the endpoint is that the climate issue is only fully resolved when emissions go back to zero, anthropogenic emissions. Now, there's still an enormous carbon cycle that's going because of the natural system, but the bit that we're adding has to go back to zero. There's only two ways that can happen. We can either stop using fossil fuels, but we forget that they constitute 80% of the energy system today and are likely to, at least a very large portion, for all of this century and beyond. Or we can use the fossil fuels to keep powering the world that we live in, but we have to capture and store the CO2. So these are the choices that we have. These are very difficult choices to make. So one of the things that Shell does is it likes to look forward with scenarios. And I'll just finish on this note. We published some new scenarios in the middle of last year. And for the first time, they looked right out to the end of the century with all of the uncertainty that the end of the century might have. But one of the things by looking out so long, it actually allows you to think about the resolution of this issue, because it's not going to get resolved through to 2020 or 2050. It's on the time scale of this century, maybe even a little bit beyond. And if you look out towards the end of the century and you think about the things that have to do, and you think about the rate at which technologies can turn over and the rate at which new infrastructures can come into the system, it is feasible to resolve this issue. Now, this isn't quite 2 degrees C, which is a concern, certainly after what we've heard about the ocean system and the impacts that climate may have. But it is a resolved issue where what's happened is that we've met all of the world's energy needs throughout the century, and through the very substantial use of carbon capture and storage, managed to bring emissions back to zero. So we think this is possible. And we did another scenario called the ocean scenario, which looked at a very different type of evolution of the energy system, one in which CCS came much later. And not surprisingly, it ended up with an even higher temperature. So we think that it's important that this technology comes in as early as possible. And that's a risk. It's a risk that we're not talking about the right technologies today in the climate discussion to actually resolve the issue. We're talking about other things. So, key points to finish off on. Managing this issue is about managing a whole system that's going to take, that's already running and is going to be running for the rest of this century. It's not about where we need to be in 2020, although that's a lot of what you will hear in the political speak. Governments will progressively act on this, and that means that there's a risk to all of our businesses and to the costs that they may see and how they operate throughout the years to come. We need to talk more about carbon capture and storage if we really want to manage this risk at all. And we have to think about how do we actually get to a net zero emissions. And we need to rapidly deploy And whatever we do in this, it's going to have to be something that we do relatively quickly because we are running out of the time. So thank you very much. For those that listen, there's always the Shell cautionary note. And I will finish on that. Thank you very much.
All right, well, thank you, everybody. We've heard three experts in their areas talk about three very different issues. While you're thinking of questions, I'm going to start. John, I like your description of a climate model. I was hoping you could tell me what they're good at, and I think you showed some, what they're bad at, and how. I know the government, many governments are spending lots of money trying to make these climate models better. What would be your top 1 or 2 ways we could make the climate models more useful?
Oh, gee, how to make them more useful? Well, the biggest problem with climate models right now is that they can simulate things on a fairly large scale, but there are important aspects of the climate that happen on a very small scale. In particular, the reason we can't really pin down using climate models how sensitive the Earth is to the amount of greenhouse gas emissions is because there's another thing that we're doing to the atmosphere at the same time that has a compensating cooling effect, and that is putting small particles into the atmosphere, mainly from coal-fired power plants, but lots of other sources as well. And those interact with clouds on a microscopic scale. They can make clouds brighter or dimmer. They can make clouds last longer or shorter. And to really, that's something happening at a microscopic scale. It's nothing that a global climate model is going to be able to deal with on a large scale. So I don't think that we're really going to be able to get the climate models much more accurate in the near future in the decision time that we have available to us. What we are going to be able to do is with continued observations of the climate system from satellites or from aircraft and so forth, pin down some of those processes and understand, okay, the models are doing this, but they're missing this process, and if we can estimate the effect of what they're missing, then we can narrow down the range of uncertainty. And right now, one of the big uncertainties is exactly how much of a cooling effect we're doing with the particles, which is bought us time in the sense that the climate hasn't warmed up as much as it would have without that effect. But sooner or later, if we clean up pollution, we're going to clean those up also, and we're still going to be stuck with the carbon dioxide.
Yes. And as we know, carbon dioxide stays in the atmosphere a long time. And that was one of David's main points is over the next century or longer, we're going to keep burning fossil fuels. It's really just a matter of time. And Richard, your talk was also was a little bit depressing. But one of the things that David, when he talked about this in our class today, he was basically saying that energy efficiency measures, while good at saving money, don't change the long-term forecast. They're just sort of delaying the warming. But I was wondering, Richard, if you could think how delaying the amount of CO2 in the atmosphere, the rate of change, how important is that, do you think, in this ocean acidification problem? How can these ecosystems respond if there's...
Well, the ocean system responds on fairly long time scales. As I mentioned earlier, it takes about 1,500 years to go through a single circuit of the oceans. And in order to neutralize the CO2, it has to go through many of those circuits, such the oceans, to neutralize the amount of CO2 that's been released thus far, would take in the order of about 30,000 years or longer to neutralize that CO2 and bring it back to the pre-industrial levels, as much as 100,000 years. So minor adjustments to the CO2 emissions that we have been discussing so far, they don't play a large role in how the ocean responds. It's the total amount of CO2 that's absorbed by the oceans that's important on on the climate
Okay.
climate sales.
All right, I'm going to take an audience question for David. This is from a student. How would you suggest developing countries, the BRIC countries, should reduce their carbon outputs? They have the same opportunities as the West to go through their own industrial revolutions.
So that's a really good question, and it's perhaps the crux of the international climate negotiations, which is, well, you've all had time to develop your economies, now it's our turn. I think one of the difficult choices that many countries face is that the easiest way to provide quick, large-scale access to energy is to use coal. That's typically where they start. And it's affordable, it's widespread, it requires a relatively low technology base, and off they go. The answer to this question is perhaps, as I said, at the core of the negotiations. And what's happening is that people seemingly think the answer is, well, if we subsidise them enough, they'll leapfrog this and grow with a different energy system. And I don't think that's going to be the case. I think what we really have to do is concentrate on the very largest of the developing countries. And really they're rapidly emerging economies now. They're extremely wealthy. And they do have the necessary resources to tackle this problem. And the big ones are China, India, and the Middle East countries. I think it's less of a concern in Africa today. If you look at the African economies, even if they grow rapidly over the next sort of 30 years, the amount of CO2 that's likely to be produced there is still relatively small. So there's a time dimension there. China I think has already recognised that carbon capture and storage is in its future. It's starting pilot testing on this technology. It's trying to develop carbon pricing in its economy. And these are the two precursors to recognising that it has things to do. In the meantime, what it's doing is it's investing as much as it can to at least minimise the coal use through first of all through natural gas, and then through nuclear and wind and solar.
Yeah. One of the things, interestingly, the United States carbon emissions have gone down the last few years, and it's because the price of natural gas has dropped. And natural gas, making electricity from natural gas compared to coal cuts your CO2 emissions in half. And but globally, there's still lots of coal being burned.
That's right, and there's globally a lot of the coal that was used in the United States is now being burned in other places, and hence the difficulty of this problem emerges, that it's not just about immediately what your local emissions are, it's actually can you manage the global emissions.
Okay, this is for all panelists, and it says, why do we rarely hear about the benefits of climate change? This is from a faculty member.
So I start? Because right now there are basically two sides to the issue, and one is climate change is bad, and the other is climate change doesn't exist. Who's going to talk about the benefits in that context? Truth is, there are some benefits. So, for example, I've sometimes said off the cuff that we'll know that climate change is a serious issue in the United States when people stop moving from the northern United States to the southern United States and start moving back up because it's too hot in the south as opposed to too cold in the north. So there's a comfort issue. Heat and cold both cause mortality in different ways. There's a crop issue. Some countries are going to have better growing conditions, some less. CO2 is certainly a direct negative on the ocean, but if it didn't change climate, it would probably be a direct positive on the atmosphere because CO2 is a necessary ingredient for plant growth, and it also at the same time tends to make plants more drought tolerant. So yeah, there are benefits. The disadvantages outweigh the advantages, but nobody has it in their interest to talk about the benefits.
Okay, thank you. Dr. Feely, this is from a student. Has China reacted to the data about ocean acidification, considering the amount of seafood they depend on?
China has reacted mostly through the scientific community. The scientific community has responded, and they're working at the international level and working very closely. We have just worked out an international observing system from ocean acidification, and China is a participant. And also, the largest aquaculture industry in the world is in China. So they have a large concern about acidification because of its impact on aquaculture. So that's why we are interacting very strongly with the Chinese government on this issue.
Okay, this is from a community member, and it's open to the whole panel. How can Texas and the other 49 states implement more educational studies in our public schools for climate change and renewable energy? John's a professor. He might have to answer this one.
Could be. Yeah, well, I'll just speak for earth science in general. Earth science is sort of the ugly stepchild of high school science education. We've got commitment to teach biology and chemistry and physics, and then the interesting stuff gets left off to the side or is taught by a non-specialist. There's really not the community of people with earth science degrees in our teaching profession, partly because it hasn't been incentivized by having that being an integral part of our curriculum. Certainly there are places where it comes in. I think the fourth grade in Texas is a place where you can bring in that sort of discussion, but it's a sufficiently complicated issue that I think it's worth following up at the high school level, and unfortunately, there's a finite number of classes that can be taught, and you have to drop something else from that, and there's so many considerations that we probably won't see a wholesale addition of this important matter.
Okay, this is for David. Are there technologies being developed to provide a balance between energy demand and the damage to the environment? With the exception of carbon capture and sequestration, are there other technologies that you're aware of in oil and gas exploration?
So related to this issue specifically, no.
Yeah.
It comes down to the very simple the fact that I outlined earlier.
Yeah, there are some other geoengineering type
that's
schemes,
a whole
I'm going to call them.
different realm, yeah. But in terms of energy technologies, there's energy technologies that don't involve fossil fuels, and there's a whole raft of them. And then there's the set of fossil fuel technologies, and there's only one way of managing that ultimately, which is putting the CO2.
So here's a provocative question from a faculty, an alumni, and an industry person. Two of the speakers did a good job of explaining the threat of climate change to our environment. The speaker from Shell suggested the situation, would like to hear a different situation. I would like to hear the other two speakers react to the Shell presentation. Richard, would you like to go?
I guess,
I'm putting you guys on the spot.
well, I would say I'm very much in favor of carbon capture and storage. I think it is a reasonable solution, provided we can develop that technology in a safe manner in which you do not have the potential for leakage. And I think if we can address these leakage issues, that which we should be able to do, then it represents a very good approach. If you think of the other engineering approaches for climate change, they ignore the effect of increasing levels of CO2 such that they enhance the acidification effect. So on this issue, I'm with David on this one.
And yeah, I'm sort of with him. If we had, proven economic technology for carbon capture and sequestration, then we can put our eggs in that basket. Until we get to that point, and we don't know how long it's going to take to get to that point, we can still buy time by increasing the use of non-fossil fuels, at least as a temporary measure until a permanent solution is obtained.
I think that's a critical distinction. Is wind, solar, biofuels give us more time to implement this carbon capture and sequestration. Here's a question for David. from a student. How realistic is it to expect the widespread implementation of carbon capture and storage? And have other companies in the oil and gas industry also invested in this option?
So all of the companies in the oil and gas industry, to some extent or other, are investing in this in some form or another. So this is a vibrant set of technologies that, frankly, the oil and gas industry could deliver, and it could deliver at increasing scale if the political situation is there, so a carbon pricing mechanism or some political signal to actually do it. Can it be delivered on scale? I think it's an industry that has a history of delivering on scale. If you look 25 years ago, people said, well, liquefied natural gas, that's a pipe dream. Nobody's ever going to be able to deliver that on scale. Today, it's a huge industry globally with hundreds of ships traversing the oceans all over the world, moving gas from parts of the world to another. The US today is actually building LNG facilities to export gas.
Right.
That was something that 25 years ago was just seen as, oh yeah, nobody will ever do that.
I'm going to interrupt.
Yep.
Okay, since we have about 15 more minutes to go, this is to any panelist, can nuclear energy be one key solution to mitigating climate change? We haven't talked about nuclear.
I think nuclear has huge potential. It's baseload electricity, which is what the key issue is. 24/7 energy without issue. But if we think carbon capture and storage has some concerns, just look at the concerns that you have when you go to build a nuclear plant today. I think it's a very viable technology. Many people have a lot of issues with it. And so I think the idea that can sort of be rolled out on a very large scale globally in a very short space of time has huge issues associated with it.
Excellent. Who will pay for carbon capture and sequestration? Taxpayers, oil, gas, coal, since they provide, their product creates so much of the waste. I think you have a short answer to this.
Energy users will pay at the end of the day.
The consumer
for this
will pay.
Technology, the consumer will pay.
Yeah.
Yep.
Here's one for Richard. If the oceans are warmer and CO2 solubility decreases, how is acidification occurring?
The increase in concentration of CO2 in the atmosphere from fossil fuel burning far overwhelms the very small changes that would be due to warming. And you can see this in the most recent IPCC report. It is a small change, it's a few percent, but the addition of atmospheric CO2 far overwhelms it.
Here's a question. We keep talking about coal because it's the least complex and dirtiest burning energy source. What other steps are taken to get energy from other sources and possible future steps to eliminate coal use?
So that really comes back to the whole energy story. I would suggest, there's a bit of blatant advertising. Go and have a really good read of the Shell scenarios that I talked about, because they just plot different trajectories for the whole energy system. I think that's really the answer to the question.
Okay.
But have a look at some of the other energy companies and energy institution scenarios as well, because they're very revealing.
Dr. Feely, at what pH will plankton die off?
Well, you can go to, for example, some of the Yellowstone, and you can go there and you will see certain kinds of phytoplankton existing at very, very low pHs. There'll be a completely different species, of course, which means that there will be some species that can live in low pH waters and other species that cannot live in low pH waters. And the ecosystem is based on which phytoplankton can live in the oceans. So it's our job to determine how the ecosystem will change and which organism will be affected and which ones will not. With respect to the organisms we've studied thus far, in a very short time frame, the last 15 years or so, about 50% of the organisms have been studied show a negative impact. 25% of the organisms see a positive impact, and 25% of the organisms see no impact. So that represents a very significant change to the ecosystem. How that will work itself up through the food chain, we're still trying to figure out.
Okay, this is for John. More than half of the adults in the U.S. believe climate change, if real, is not the result of human activities. Why do you think this is the case?
Well, partly it's because most of climate change has not been the result of human activities. And the question is often formulated in the sense of, which is it? And the answer is generally all of the above. Everything is affecting the climate in one way or another. And so the issue is not, is it or isn't it, it's a matter of degree. And the way that the public discussion has come out is essentially, here's a set of beliefs on one side and here's a set of beliefs on the other. And people are continuously, well, the people on this side are getting their information from a different set of sources than the people on this side. And those sources are telling what seem to be consistent stories. And so it's not that people are hearing the same evidence and coming to different conclusions. They're actually hearing different evidence.
All right, I got a note that says www.uh.edu/uhenergy. You will find all the presentations and the film of this event. I should mention that David has a blog, as well as John's 2 blogs. Richard has a nice website. I'm going to post a blog about this event. Is there a machine that could scrub CO2 from the air? Available?
Yes, no.
Okay.
So in theory, yeah, you could apply various processes to extract CO2 from the air, and there's lots of research going on about this. But then you have to do something with it, so it comes back to carbon capture and storage. I think pictures of this have appeared on various science publications, Popular Mechanics and things, as these sort of elaborate and glamorous plastic trees sitting in the air. I suspect if we ever built one, it'll be a great, huge refinery-looking thing, just like all of the other industrial processes that we build.
Yeah. One exciting thing we talked about in our class is that if there is a appropriate reservoir to store CO2, that the folks in Houston and Texas know how to build pipelines to bring that CO2 to us to put in the ground.
Comes back to the oil and gas industry. Very efficient.
Here's a related. What is the outlook on jobs and job security for the environmental field in the private and government sector? This is obviously from one of our students. How about all 3 of you answer that one? Jobs in environmental and climate change.
Well, we have, for example, a undergraduate program in environmental sciences at A&M. We started it about 5 years ago, and or a little bit more than that, and it now has about 300 majors. And when we started, we wondered, well, we know students are interested in this, but will they actually be able to get off the government payroll in the future with real jobs? And it turns out they are. They're getting jobs in all sorts of different areas, from air pollution to state agencies, to consulting companies, to urban planners, because environment is involved in so many different areas. There's actually a wide range of jobs available.
But I think, so a slightly different tack. I think the real solution has to be that the people that build projects in the first place and the people that work right through the industries that do produce various emissions out to the atmosphere, this is part of their DNA. And that, that's where we have to get to. I think having specialist environmentalists is good today, but they have to be the project technicians of the future.
Yeah, and I think the real science innovations are going to be in adaptation and mitigation, and there is where we'll probably put most of our energy in the future, is to developing those new technologies, and the young scientists that are coming along have the ability to develop these technologies in a way that it will provide new economies. And I think this is the direction much of the science is headed, and this is the direction where we will move forward within the university systems.
Here's another one for Dr. Feely. There's always a changing projection of a critical or no going back date. It used to be around 2050, the date when sea level rise and ocean acidification really start to see dramatic effects. What, in your opinion, is the current critical date? Why?
Well,
So this assumes business as usual, that we don't do anything going forward.
the reality is that all the models seem to show that the impacts on terms of the CO2 emissions don't differ very much between the different CO2 scenarios out to 2050. When you go from 2050 to 2100 is where you see significant differences between the CO2 emission scenarios. So the decisions that we make now, which will affect those CO2 emission scenarios by 2050, are decisions that are very critical because they impact where we go from here on throughout the rest of the
I
cycle.
think that's a real important, and yes, and as David said, it's going to take a generation to get carbon capture and sequestration scaled
Yeah.
up. There's some pilot projects, but it's really...
So we're at that point, and if we can't decide within this decade, it's really going to become not a lost cause, but a terribly difficult problem to catch up on.
I think that's a great place to stop. I know...
Sounds a bit depressing.
But I think, well, John, would you like to comment, last word on sort of this critical date, or what's...
Well, it always seems to be about a year from now until we have to do something, and then the next year we have to do something. The problem is there's no critical date because there's no critical threshold that we can specifically identify. Each domino is going to fall at some unspecified time within a range of 30 or 40 years. We don't know which one's going to go first. So basically, no matter how long it takes, anything we do will eventually have some benefit. It's never going to be too late.
Thank you very much. And let's thank our panel. And
I just wanted to thank our panel again. It's been a great discussion. I've really enjoyed it. Remember, March 4th is our next one, renewable energy. That should prove to be very exciting as well. Thank everybody again, and I hope we see you March 4th. Thank you.